Folks, we're having some technical difficulties, so we're going to be getting started in just a minute. Please bear with us. We are having trouble joining one of our speakers to the webinar. Folks, we're waiting for our main presenter to be able to call in. So we're expecting to start soon, but we are experiencing some unforeseen technical issues. So we'll try to get started as quickly as we can. All right, I believe we've acquired Jamie, so we should be able to get started in just a minute. Jamie, are you with us? You're going to need to unmute.
Yes, can you hear me now?
Yes, we can hear you. Sorry, everybody. Sometimes technology, as much as you want it to work, it just doesn't work, but we're all set. So at this point, we're going to get started with the day, and I'm going to hand things over to our wonderful colleague, Leah, from the SNP Network.
Thanks, Tess. Good morning, everyone. Thanks for your patience. And thank you for joining us today for the training Designing Green Stormwater Infrastructure, brought to you by the Stormwater Innovation Center at Roger Williams Park in Providence, Rhode Island, and the University of New Hampshire Stormwater Center and the Audubon Society of Rhode Island on behalf of our SNEP network. My name is Leah, and I'm the Policy Assistant with the New England Environmental Finance Center and a member of the SNEP network. The Southeast New England Network is a collaborative group of technical assistance and training experts based in Rhode Island, Massachusetts, with a focus on how to finance and implement stormwater and watershed management efforts. Our network is supported by EPA Region 1 with a farsighted vision to build resilient ecosystems and connect communities through action, collaboration, and innovation. The network's mission is to empower communities by building local capacity to achieve healthy watersheds, sustainable financing, and long-term climate resilience through stormwater and ecological restoration projects. And there we go. To learn more about or request network services, SNEP communities can visit our online portal on the SNEP network website. And you can fill out the request form for technical assistance. You can also contact our two state liaisons, Kimberly Groff from Massachusetts or Elizabeth Scott for Rhode Island, with any questions related to the SNEP network assistance. And you can visit our website, snepnetwork.org, to find out more. And before we begin the presentation, I want to draw your attention to the GoToWebinar questions dialog box. Please type in your questions at any time during the webinar, and we will have breaks periodically throughout the training to answer questions that are submitted in the questions dialog box. And with that, I'd like to introduce our great guests for today's training. Today we have James Houle, the Program Director for the University of New Hampshire Stormwater Center. We have Meg Kerr, Senior Director of Policy for the Audubon Society of Rhode Island. We have Brian Burns, Deputy Superintendent of Parks and Recreation for the City of Providence. And we have Ryan Kopp, the Stormwater Coordinator with the Audubon Society of Rhode Island. So thanks for being here today, and I'll hand things over to Meg to give us a little more context for the training today.
Great, thank you. Good morning, everybody. Sorry about the technical difficulties. I'm just going to give a brief introduction to the Innovation Center and Audubon's role, and then turn it over to Brian to dig a little bit deeper into the Innovation Center. Audubon, for the past 5 years, has been a member of the Green Infrastructure Coalition here in Rhode Island. This is a coalition of over 40 nonprofits, government, business groups that have come together to promote green infrastructure. We have 3 overall goals for the Green Infrastructure Coalition. First, to work with cities and towns to get sustainable funding for stormwater management through a stormwater utility or an enterprise fund. Secondly, to ensure that as we are promoting and doing more and more stormwater management, that we use as much green as possible. And third, as we're doing all this work, to use it as a way to build a local workforce that can do the green infrastructure work. Early on in our work together as the Green Infrastructure Coalition, we identified maintenance of green infrastructure as an ongoing challenge. I always like to remind us all that maintenance of all our infrastructure is a challenge in this country. It's not just a green infrastructure problem. But we partnered with the City of Providence with Brian on doing some green infrastructure maintenance trainings at Roger Williams Park, where there are 40 stormwater practices installed. And through that collaboration, the trainings were successful. We've been learning a lot. And we were introduced to Brian's vision of creating a Stormwater Innovation Center at the park, utilizing the city's investment in green stormwater. And we're thrilled to be working with Brian, with the Nature Conservancy, on moving forward with implementing the vision of a Stormwater Innovation Center at the park. And we also very much appreciate the support that the SNEP network has provided to this work, providing a platform for this training, for example, and other investments that they're making in the Innovation Center. So I'll turn it over to Brian to give us a deeper introduction to the work that's going on at the Innovation Center.
All right, I think we're all set to go. Can you see my screen? Okay, so we're good to go? We're good? All right. So thank you, Meg. Welcome to the Providence Stormwater Innovation Center. We are happy to have you here for this training today. We're excited to have Jamie here to talk about what he's been working on his whole career. The Innovation Center was born out of a consent agreement signed between the City of Providence and Rhode Island DEM back in 2017. And what the Innovation Center is a partnership from many different stakeholders in stormwater management. So through that partnership and the ability to engage with different people involved in stormwater, we are able to innovate stormwater practices, not only here, but hopefully throughout the region. And our intent is to document what we're doing, innovate what we're doing with stormwater, and then educate people about what we've learned and what we're doing, and then train. Because as Meg mentioned, maintenance of these stormwater things is as important as the construction, if not more. So there are 42 green infrastructure BMPs in Roger Williams Park. Roger Williams Park is 435 acres. 100 of those acres are covered by water. And we are in the middle of the city of Providence, so we are in an urban area. Back in 2014, a water quality plan was created, and that was our roadmap to improving the water quality here in Roger Williams Park.
Brian, I'm not sure your slides are progressing. At least they are not on my screen.
Okay. How about now? You see it?
Yes. Yep.
Okay, so those are the four, thank you, Meg. Those are the 42 green infrastructure BMP locations in the park. And the waters here are impaired. There's a TMDL for phosphorus. And through the consent agreement, we are looking to reduce our phosphorus loading to these waters by 85%. The ponds in the park are also fed by 3 other waterways and a pipe that runs through urban areas. So all of that contributes to the low water quality here in Roger Williams Park. The projects, 42 of which were completed in 2 years due to a funding deadline. We had 5 years to do it, but we did it in 2 years. So we had a good group on that construction project between the consultants and the contractors, and we were able to work it out. So what did we learn? Throughout the process, which was a 3-phase project, we continued from phase 1, doing what would normally be designed, to much change design by the time we ended over the 24 months. Some of the highlights, we looked at how the water should pass through these BMPs. So there's 2 school of thoughts from what I've been learning. One is use a street or roadway as the overflow. So allow the low flow in and let the high flow go by your BMP and use that as an overflow. The other one is to bring all the water into the structure, provide an overflow pipe, and let the water flow back the same way it would as if it was bypassing it. So 2 very different schools of thought based on 2 different designers' opinion of what should happen. Overflow pipes, sometimes you'll see them just sticking out of the middle of an infiltration basin. We've kind of tried to hide it a little more, maybe putting some landscaping around it. In this picture on the right, you can kind of see how we blended it into the slope. But one of the most innovative things I think we've done is related to sediment control. So on the left-hand side of the screen, you can see what is a river rock swale. You can't see much of the river rock because it's totally inundated with sediment. And that's been our problem. River rock looks beautiful when it's clean. When it's not clean, you don't even know it's there, and it's extremely difficult to maintain. So through this innovation process, we've actually developed 4 bays out of precast concrete pavers, permeable and impermeable, and we're testing how they work out. What this does is on the right-hand side, you can see that BMP is very close to the roadway, so our maintenance personnel can literally drive by these BMPs, see if there's sediment in the basin, and easily with a power broom clean up that sediment, as you can imagine looking at that picture on the right, before it gets totally inundated in 12 inches of river rock, and it's much more difficult to remove. So that's one of the biggest things we've talked about. We've also looked at scuppers, using scuppers through city walks, where commonly if there's a walkway, a scupper's not utilized, but we've come up with a good development on that. A lot of construction organization and operational things. How do you keep these BMPs offline during construction? How do you get the vegetation to grow in without being flushed out by these big storms? And that's what we've been finding, that we don't get the moderate storms anymore. We get the 2 to 3 inch storms in an hour, and it's almost impossible to control. So keeping these on for moderate flow just doesn't happen. So how do you stop the water from flowing into these in those heavy rainstorms? Erosion control fabrics. We looked at a bunch of different fabrics, and we've installed a bunch of different fabrics in the practices and now monitoring those types of things. One of the things we learned is it's critical for jute mesh and those types of fabric, erosion control fabrics, to be installed prior to broadleaf weeds starting to propagate. When and if you're doing it within the seeding season, and DOT it's till April 15th, that's fine. But if some construction projects delay, they get in, the broadleaf weed pushes those fabrics up so that the vegetation doesn't grow through it. It gets pushed up and it's no longer functioning. So those are some of the lessons that we've learned. So what's this all about? Well, here at Roger Williams Park, not only are we a petri dish for stormwater management, because we have hills, vegetated areas, non-vegetated areas, roadways, shallow water, high temperatures, impaired waterways. Not only do we have all of that, but we have facilities here to offer classroom trainings, and then 42 stormwater sites where we could take those classroom attendees out into the field, have them pull invasive weeds, have them clean river rock. We've done several trainings so far. They were extremely successful. We've had our maintenance personnel go through 3 or 4 of them here in the park, and they're now well versed in the maintenance of those things. Other things always come into play, like COVID, that affect the maintenance that we do to these stormwater things, but at least we've educated these crews and they know what to do and how to do it. So the other thing we're doing with the center is the water quality monitoring. We need to know if these BMPs are working, and we are testing single BMPs. We're testing the inlet to the ponds here in the park and the outlet. And it's a very important thing to know if what we're actually doing is working. We can build all of them. If they don't work, there's no point. So the other thing we find is that there's often money to build these BMPs, but not a lot of money for maintenance or monitoring. So we've had to be creative in funding to find a way, through grants or otherwise, to monitor these BMPs to make sure that they're working. But that's part of the center too, working on that. So innovations in stormwater design. We want to know what you all are dealing with. If you're a landowner or a municipality, we want to know what you've done in your backyard or in your park to create better stormwater. And that's what it is, collaboration. We want to bring everybody's ideas together, get together, talk with everybody about what they're doing, what they see. Send your information into us. We'll bring it to a common place that's globally available to everyone. And then if you get a consent agreement, you don't have to start from square one. Hopefully we can get you to square 10 before you have to start your projects. On the slide you're looking at now, to the right is the seal house. Way back when, Roger Williams Park Zoo had housed their seals and sea lions there, but the building cantilevers over the waterway. So a lot of our monitoring equipment is mounted inside this building, goes right through the floor into the water below. So it's a perfect setup for that type of testing, and it's been very successful. When they built the building back in 1893, maybe they had the stormwater in mind, I'm not sure. But that will be a kiosk, not only for research, but for outreach to the public, for education. We'll bring students into the seal house, show them how it's working. There'll be video screens running with some of the stormwater things we've done and how they work. So we hope to make that a location for people to come and learn about stormwater. So this photo, prior to my tenure here over the last 5 years with the City of Providence Parks Department, I was a contractor building stormwater BMPs and other site construction projects throughout New England. And this is the street outside one of the BMPs we installed. This happens to be a sand filter. But that, every time I see that picture, I get a little palpitation in my heart that that's a lot of water, and that's what we're dealing with now. That's a 2 to 3 inch storm within an hour, and we have a very difficult task. And if we don't keep innovating, I don't believe that the practices we're using now are going to work. So that's what this is all about. And we are very lucky to have Jamie Houle from the University of New Hampshire Stormwater Center. here to talk about designing green infrastructure and how we can do that better. Jamie has spent his career working on that, and he's well respected in the field, and we are very lucky to have Jamie here today. So I'm going to turn it over to you, Jamie. Thank you very much.
Okay, thank you very much, Brian. Yeah, it's great to be working with Brian and Meg and their team. Can you see my screen okay? Good. All right, and I was kind of joking with Brian up until about 3 months ago. I owned and operated the largest research facility for stormwater in the Northeast, and now I have to kind of hand that over because we only have about 12 systems at any one time that we're actively monitoring, and I think Brian has about 42 or so. So great work, and of course implementation it's great to be here, and it's great to have a site like Roger Williams Park that when we implement, we often make mistakes, and we don't always have a public showcase to learn from those mistakes. And so it's good to be working. I think these types of demonstration facilities are critical to advancing the practice. So I'm going to jump right in. This is a lot of content here. Essentially, we have a 40-hour stormwater design course for our students here at the university. And in many respects, I take that 40-hour course and condense it into 2 hours. So obviously, we're not going to be able to go over everything, but I'm going to try to touch the highlights on, some of the learnings to date and where we're going, what we've learned, and we definitely have made some mistakes. So again, we want to stand on the shoulders of the previous mistakes so that we don't repeat them, which is kind of the general mission of the Stormwater Innovation Center. So I want to talk briefly about hydrology. We're not going to cover hydrology. The assumption here is that you understand the basics of modeling, developing hydrographs, and routing it through your system. Obviously, the players here are the size of your drainage area, the land use, the precipitation patterns, and particularly the design precipitation. Oftentimes in stormwater, we're dealing with the small frequent storms, the 1-inch storm, and there's contingencies for either controlling peak flow on the larger events or just passing them safely and stably through the system. So we're not generally managing the 100-year return event. Obviously, the watershed characteristics and the land use characteristics and the precipitation, particularly design precipitation, dictates the hydrology that you're designing for, and also in there are regulations. And one of the interesting thing about making this type of information available is I'm sure if you're in the field, you found, I think we all found that the science is pretty fast and changing pretty dramatically. And in New Hampshire, our stormwater manual was passed in 2008, and that was probably a 5-year effort to develop that manual and get it into statute. 2008 is ancient now, so lots happening largely from the learning from the increase in implementation. So I'm going to just at liberty skip over some slides. Just I apologize for the delay in the beginning. Obviously, the hydrology, you're going to need some additional land characteristics, things like slope, and I'll talk a little bit about slope as it pertains to system design as well. And then flow path, typically we're calling that time of concentration. It's one of the biggest errors we see when we review plan is people misinterpret the time of concentration. Oftentimes it's noted as the longest distance in the watershed, and that's not really the definition. It's really the longest hydrological flow path. So for the most part, at least in the hydrology, that's one of the biggest issues we see. And then beyond that, what we see in the issues in modeling are kind of like not honoring or adhering to pre-development subcatchments. So one of our design intentions, obviously, is to maintain the pre-developed condition to the extent possible, and largely hydraulically, or hydrologically, sorry. So what I mean is, oftentimes what we see is you take your site, and then where you want your stormwater feature is often known, and so you delineate your site, and your point of analysis is where you want the discharge for your developed condition. And what that sometimes does is it ignores the existing drainage areas. And what I mean by that is, oftentimes, if you're discharging it to one single point, you have to evaluate whether that's where water was going. And if you're increasing the flow regime there, does what you're discharging to have the capacity, or is it going to, are you going to run into problems either from adjacent property owners or existing structures like culverts? Alternatively, you could be stealing water from, say, wetlands or other sensitive habitats that had previously gotten some of that flow. And so that's one of the things that when we review plans, we often find is certainly in a developed condition, that's not an issue, but particularly for new development, that's one of the bigger issues. And then finally, not taking into consideration off-site drainage. You have your property lines, but the hydrology doesn't always honor the property lines or the political boundaries, so it honors the watershed boundaries. So you could have large amounts of water coming in from off-site. So those are the typical common mistakes that we see, so yeah, it's one of the things we'd like to address better in at least the hydrology component. Now, getting into design, one of the current arguments or haggling we have these days is with pretreatment. So if you look at many of the manuals that are out there, they all include pretreatment as necessary. Pretreatment is often a structural forebay, and it's often sized for some percent of the water quality volume, or it also often has some volumetric sizing criteria to it. And so the question obviously comes in is, as you're redeveloping or retrofitting, or even, for new development is not as big of an issue, but this idea of the configuration of the pretreatment, what does it look like? And I think we have more options than many of the manuals allow these days. If we go back to the intention of pretreatment, it's to facilitate routine maintenance. So, you want a place to take out the shopping carts and the bowling balls, the large core solids, and you want something that you can maintain easily more frequently. And so that's largely the intention. There was never a intention that the forebay offered some type of flow control or water quality and control. It's strictly a ease of maintenance. And so, we've often seen sometimes that ease of maintenance criteria, that initial attention, get buried, and you require pretreatment forebays or structural forebays. And if you've ever spent time kicking around behind shopping malls, and you look at some of these pretreatment and forebays, often behind a fence or inaccessible to maintenance, the way they're implemented doesn't always enhance that maintainability. And so we've begun, I say we, that in the scientific community, we've begun to become more flexible with what pretreatment looks like, and back off on some of the kind of more standard requirements of it's got to be structural, it's got to be some type of basin. And so things like offline catch basins are really good as pre-treatment. And I say offline versus online configuration, because for the most part, when we look at historic structures, here on the screen, this is the picture in the middle. Historically, catch basins are plumbed together in series and then discharged at some point. And when you're doing that, you're robbing the functionality of that deep sump, because you're just routing. It's possible that the first catch basin in line is working and removing sediment, but as you route water through the next in series, you're actually resuspending and moving that sediment. So you're removing the ability of that pre-treatment to actually work. So offline, which is the picture on the right, is this kind of herringbone or fishbone pattern where you have a catch basin receiving water from the top, has a deep sump, and it has one outlet basically to a main trunk line. So that's the preference these days. Not a lot, some manuals have updated this and require it, but the vast amount of existing infrastructure are kind of the middle picture. And so where we can, we'd like to introduce this new offline configuration. And if that's the case, then these deep sump catch basins serve our purpose for pre-treatment, right? So these are easily to maintain. You can vector them from the surface. They have a, at least a 10% removal efficiency for total suspended solids. And, they're serving the purpose of pre-treatment. So we've made those arguments in the past, especially where sites are tight and you don't have the luxury or the real estate to implement large pre-treatment. So the other thing, we have done some research on pre-treatment, and in particular, I want to look at this is a tree pod system, and so I'll show you a bunch of different pictures of tree filters, but this tree pod system has a pre-treatment area, and I think that's what distinguishes it from other tree filters, where water flows into this first bay, and there's a hatch right here that can be lifted up, and the gross leaves and solids that you see in the right picture can be removed. And so this is the coarse stuff. Some of the gross litter, leaf litter, and other gross solids get removed here and can be easily maintained. If you're trying to maintain these street trees or tree filters in the cityscape, a lot of times they have grates that, again, are difficult to remove. And oftentimes we don't have equipment for this, right? For the most part, our go-to maintenance is a Vector truck. And you can't really do much with a Vector truck here. So this is one of the things that I think will happen over time. We are planning a maintenance course, and I expect we'll see innovations in maintenance tools as we understand the maintenance. Right now, I think it's I can say pretty safely that in general, the go-to maintenance operation is just neglect. That's not everybody, but for the vast majority of stormwater treatment systems in there, I know I've written a bunch of operation and maintenance plans, and I know exactly where they go when we hand them over. Oftentimes too, I don't absolve myself of guilt here, because the first operation and maintenance pages were like 60 pages long, and who is going to read that? We're trying now to reduce it to a single sheet, something to the effect like, can water get in? Can water get out? Are there visible signs of flow obstruction? Something that simple, right? And certainly Brian and his team are helping out. This idea of drive-by inspection, I think, is probably going to be really compelling to many municipalities. But pre-treatment is there for a reason. So when we have this hatch and we can easily maintain it, we see this is the data for this study where we looked at the removal effectiveness. For sediment, we got a 26% removal. So oftentimes we assume a 10% removal. Here we're talking about a 26% removal of the total solids. 9% hydrocarbons. There are some sediment association between hydrocarbons and metals. So if you're removing sediment, you're removing some of this material as well that's absorbed to it. And then about 11% phosphorus and not much nitrogen. Nitrogen tends to be highly mobile, and so not easily trapped in these types of structures. So there's good evidence that pre-treatment works, but we have to be a little bit more flexible of what we allow for pre-treatment. Here, if you look at this particular system, I mean, there's no sizing here at all. This is a hatch that opens up that gives you accessibility to this sump. So, you know, this is not 10% of the water quality volume here. This is just an accessible, maintainable sump, and even a shallow sump at that, with some screened inlets. So I'll move into, essentially for this, I am only going to be focusing on the enhanced treatment systems, what we would call filtration and infiltration best management practices or stormwater control measures. For the most part, as we enter into the 21st century, if the state manuals haven't gone there yet, many of the local requirements, and particularly if you're from Massachusetts and New Hampshire, we have the pleasure of being, we don't have primacy over the Clean Water Act. EPA Region 1 does, and they've written our permit for us, which has some pretty stringent parameters around requirements for stormwater controls. For the most part, while they don't do it explicitly, implicitly, they're requiring filtration and infiltration BMPs because they're requiring increased removals of sediment, phosphorus, and nitrogen. And certainly, if you're in the stormwater game, you've probably witnessed in your career this really transition from a huge focus on TSS and sediment to now a larger focus on bacteria and nutrients. So nitrogen and phosphorus. So we're a long way away from where many of these manuals were written, and most of the water quality guidelines now focus on nutrient control. So if you're coastal, it's nitrogen. If you're inland, it's phosphorus for the most part. So I'm going to focus on filtration and infiltration BMPs, and that's largely how the rest of this is going to really be parsed out. I should note that you know, this is a advancement on our conventional list, but some of the conventional systems like ponds do have infiltration characteristics. So when we look at the range of conventional BMPs that we're used to seeing, I mean, there are some detention structures that we're trying to phase out. Swales are largely conveyance structures now. They're not primary treatment structures, unless you're like a DOT and, you know, your hydrologic loading ratio is very low, meaning you have large areas of median in between highways, and you're treating a very relatively small amount of impervious cover in a large area in the median. In those types of instances, swales can be really effective, largely because they take on more of an infiltration role than a straight out sedimentation role. So bioretention systems, tree filters, even sand filters tend to be our go-to for filtration. And again, these can take on so many different iterations. They can be beautifully vegetated. They can be sparsely vegetated. They can be unvegetated. They can be grassed. For the most part, we envision that the primary function from a water quality perspective is the physical filtration through the soil media. And that's where we pay attention to. That's not to discount the planting regime. As I said, there can be so many ancillary benefits from your plant selection. There's less research on, I guess, the benefits of the plants and how they enhance treatment than there is on the soil side. And that's just a state of the practice. It's a huge gap, I think, in the research. We have to be looking more at the vegetation, and quite honestly, maybe identifying vegetation that hyperaccumulates our pollutants of concern, but there's a lot of work to do there. And then infiltration BMPs would be, things that reintroduce water back into the ground. They could be basins that in good soils. They could be subsurface infiltration systems that store water in voids in stone, voids in pipe, voids in, now they have concrete boxes. They have these milk crate containers, if you've seen them, right, that provide a loading function. And just all they're doing though is increasing your void space. So somehow you're developing void space in the subsurface, you're dumping water there, and you're relying on the three-dimensional exfiltration properties of your native soils to get rid of the water. And I'll have some slides on this where we're finding that the infiltration systems way outperform, in the field, they way outperform our design expectations. All right. So bioretention, I think, are the primary systems we see from a filtration perspective. And again, it should be important to note that filtration systems, they're typically volumetrically sized, and they can infiltrate and they may not. So they're versatile in that you can put them in areas where you wouldn't put infiltration systems, say areas where you have concerns about contaminated groundwater, or you have concerns about just the general geology. It might be a karst, or and if you're in Pittsburgh, you're concerned with acid mine drainage, and nobody's putting water into the ground. So in this case, these systems would be lined either with a compact soil liner or a HDPE liner, but you still get the filtration function. If you're putting a bioretention into a good soil and you're anticipating a lot of infiltration, then that infiltration will really dominate the performance of this system. We see that the hydrology of these systems dominate the performance. And for the most part, this is another area of research, and I'll get into that when we get into infiltration, but there's lots of preclusions on infiltration. And for good reason. There might be some over conservativeness on that. My feeling is a lot of the, stormwater is a funny field, right? Because it's not, we didn't just emerge, we're emerging. And for the most part, we exist in between other water utilities. So we beg, borrow, and steal from the wastewater industry. And a lot of our standards are adopted right out of septic system siting requirements. And so we're in the process of kind of like becoming a real entity. We're still the little wooden utility. And hopefully one day we'll wake up and be our own. And so I think that's what I want to cover there. Sometimes you hear bioretention used, rain garden. Typically, the differentiation here is rain gardens tend to be small and non-engineered, so there's no real overflow. There's no influent and effluent contingencies. It's a less engineered, more residential option that we don't really pay attention to things like the particle size distribution or composition of the soil. If you're treating with a bioretention, if you're treating large drainage areas, then all those things are coming into focus because you're concerned with that your system operates hydraulically. Otherwise, you're flooding out properties. So if we're just treating rooftop on a resident, the design contingency there is far reduced as the threat is reduced. And then tree filters are different, and they're typically not sized for volume, so they're not volumetrically sized. They're flow rate size. So they're high flow rate filters, and we need to pay attention to that flow rate because that's what the whole system is designed around. So it goes without saying that there's a lot of cooks in this kitchen. And if you just Google, and I do this routinely, you Google bioretention design, you know, the 381,000 results in 0.03 seconds. And some of them are going to work really well. Our friends in Connecticut pop up very easy, very quickly here. They've got really good updated manual and standards, but you'll also see a range of different criteria. I don't know how many of them are tested. You have old criteria, some things work, some things don't. So we're in a little bit of a transition stage where we're replacing some of the old Maryland manual standards, because let's face it, for the most part, if you're opening your design manual from any state, you're seeing pretty much the majority of content that comes right out of the Maryland manual that Center for Watershed Protection did for Maryland, the birthplace of LID, 30 years ago. So not a lot has changed, although we're slowly updating the standards. But if you've been involved in updating a manual, it's not an easy task. You don't just write it and put it on the web. All right, typically, these are the components of the bioretention system. Again, you have a forebay. Here we're showing a structural forebay. This is kind of like our own schematics here, and cartoons are a little bit antiquated, right? Because we're showing a structural forebay. I've already gone over the fact that we look at the forebay and pretreatment a little bit more flexibly now. It could be any pretreatment structure. Could be a hydrodynamic separator. Could be an offline deep swim catch basin. But whatever, that then goes into your main treatment cell. That treatment cell largely consists of a thickness of soil. Oftentimes, I've seen it be as small as 12 inches, as large as 48 inches. For the most part, since this is physical filtration, the majority of the removal happens in the top few centimeters of the soil. Very quickly, that top of the soil becomes sort of a confining layer. It throttles your system for the most part, and it also does much of your physical filtration. There are other things that occur within the soil mix, like absorption of phosphorus in the organic matter. So there are specifications for organic content. Again, you'll find this varies throughout state to state. But what we should be not doing, and I think Rhode Island's still trying to change this, is we should not be sizing these for a preset saturated hydraulic conductivity. The Maryland manual basically states that no matter what your composition of bioretention soil mix is, you model it as a 0.5 inch an hour infiltration rate. And that's just not, it's not true, it's not accurate. Many of our systems are dominated, our media is dominated by sand. For the most part, we typically see in-field infiltration rates of anywhere between 20 and 40 inches an hour after installation. So obviously, setting that threshold, that 0.5 inches an hour, it basically artificially increases the size of your system, makes it humongous, and it limits some of the flexibility with respect to implementation. So I'll have a little bit more on soil. I think I have to pick up the pace here. Below the soil is often some type of reservoir. So it's a reservoir course. We do not like to see geotextiles in the vertical cross-section of our system. So if I had a geotextile, this is very common, and this is if you're reviewing a plan, and again, this is detailed in the Maryland manual as well in their schematics, you would have a geotextile that basically act as a setting bed. It bridges the coarse materials that underlay the fine soils, and it prevents particle migration. It also is likely the smallest aperture area in your whole entire cross section, and again, that smallest aperture area is where clogging is going to start. So we see within 8 months a blinding front start on a geotextile. We have better luck with woven geotextiles, which is interesting because if you look at the hydraulic capacity of the file of the geotextiles, you know that a non-woven has a much higher rating for infiltration capacity per square foot area. I like the woven materials if they're accessible because they tend to be non-uniform. They have non-uniform apertures, and that, in our experience in the field, that lessens the potential that it's going to blind over the entire surface. So regardless, you have a reservoir, give place of water to store, and you can accentuate infiltration if it's around through an elevated underdrain. So we play with just the placement of the underdrains if we want to enhance infiltration. And I will say we do this even in soils that we don't anticipate a lot of infiltration. And I'll go into that a little bit later as to the reasons why. There's really 2 reasons, and I'll cover that later. So just cruise through some pictures. These are some of our early attempts at large structural areas that treat large drainage areas. This treats about an acre of impervious surface. We got rid of the forebay really quickly because we found it was very difficult to maintain, and we just went for a low profile, kind of like we went with a forebay, just not a huge structural forebay that was volumetrically sized. We had just a berm of stone that gave us a separation and a screening for the shopping carts. We've also been experimenting with these curb installations, and where we introduce a curb cut, excavate a depression, and nobody can still tell me why every single median strip out there is mounded. The best explanation I've heard is it's a liability to prevent cars from getting stuck, and I have seen cars stuck in bioretention systems, so it could happen. That people that pop the curb and then just their frame of the car is sitting on the curb and the wheels are spinning. So that's the best explanation I've had, but it's still, if you go to any mall, anywhere in the world, anywhere in America, you see that oftentimes these median strips are mounded, and so it becomes kind of a negative space. So it's an opportunity when we're looking at retrofit. We have a nice no-cut zone because we often see planting material just get weed whacked as people are weed whacking or mowing these areas conventionally. We've also done some installations where we just have heat flow into little bioretention planters. This particular one was done at a school as a way to save the playground. The playground, actually, it was a great A soil, but it had been compacted through all the little feet, through all, think about during recess, a bunch of mini compactors running around. It had really sealed off the top of the soil. You can see sparse vegetation out there from all that compaction and wear, and it just turned into a pond. And so we put these little planters to intercept some sheet flow, and we gave the teachers their 20 minutes of free time. Because when it rained and the playground was flooded, the teachers did indoor recess, so they didn't get their break. Other things that you see are these bump outs or these curb inlets. So this is happening a lot in the large municipalities, New York, Washington, DC, Philadelphia. They're putting these planters around the roadway. Obviously, you can see here the issue that we always see and we struggle with is you can see a very small inlet. And this is, we'll be hammering this when we do site tours at Roger Williams Park. Really small inlet, and you really need an aggressive slope because water does not like to change direction. It's cohesive, it likes to stay together. It does not take right-hand turns. So you really gotta coax it. I love me a drop inlet because gravity never fails. However, if you are having an at-grade inlet, to your system, you have to make sure that one, the opening is wide, and that slope into the system is aggressive enough that water changes direction. The other thing I'll say is this is a perfect illustration of what we see. This looks relatively new. This is not my photo, but you can see this clogging front begin right at the inlet. And once you pack some material in there, the clogging is accentuated. And so this builds up over time. This is a classic example, right? The grading was probably perfect on this. And then they put the stone in, and that stone really creates this three-dimensional filter above the design grade that starts to intercept solids, debris, and creates a clogging front. My anticipation that water is getting in the system is very low. So these are very simple things that we can correct. And the other thing here is, I can't really tell, but if I'm a drop of water, I'm looking at this grate and saying, that's where I want to go. I'm not looking at a huge turn into 180-degree turn into the system. Tree filters are out there. They are very simple in nature. And again, we're trying to do the research. Now, trees have lots of ancillary benefits. If I were to design something, I could not in my whole entire lifetime design something as amazing as a tree, something that produces its own food, sequesters carbon, provides habitat, releases oxygen. The list goes on and on. And however, we have not, in a stormwater application, we haven't pinpointed the exact functionality from a water quality perspective that the tree actually has. Obviously, it's something, but again, the filtration here component through the physical filtration through the media probably dominates the performance of these systems. Tree specification as well is something that we're working on. Myself, we generally spec out a red maple. However, there are other trees out there that we'd like to look at. Just not a lot of data here. We do have a publication that I'll link to you where we work with our urban forester to at least identify street trees that could be used. And I just cruise through here. There's retrofit potential for these adjacent to existing catch basins. This is just an example of a very simple installation that we've done, where we just dig out adjacent to an existing catch basin. We essentially backfill, or we core into it, backfill with stone, drop what is basically a manhole riser, and backfill that, connect that to the existing catch basin, backfill with stone, soil, provide our overflow riser, provide our inlet, plant our tree, and and then put a solid cover on the tree filter. We have done this in retrofit applications in order to enhance some water quality benefit into the existing landscape. And there's other proprietary devices that can do this as well. This in particular is a tree pod. We've also worked with cities to install large structures in the cityscape that, again, provides some benefit of a street tree, but also gives an area for the tree to expand and grow and provides us some water filtration benefits. So those are just some examples. If we look at design now, there's three main design methods out there for these types of structures. One is to do a dynamic sizing based on a iteration of Darcy's law. This is the equation that you see here. This is in many manuals, right, where you calculate your area of your filter. by your water quality volume, and you're multiplying it by some dynamic infiltration capacity. Again, if you're using 0.05 inches an hour, this is not going to work out in your favor. But typically what we'll do is we'll anticipate an infiltration rate and we'll multiply that by 0.5, or we take a factor of safety of about 1/2 to build in some potential clogging. That is very, very conservative, I think, and you'll see why in a minute. The other ways are static sizing, where you just instantaneously kerplunk the water quality volume into your system, and you can use it. You can develop a runoff coefficient that's in many of the manuals. I'm really loving this Philly method here, where you calculate your water quality volume only based on the impervious cover. So you're essentially not including pervious areas, and I'll tell you why. Your runoff coefficient will include pervious areas, but for the most part across the country, water quality volumes range from 3/4 of an inch to 1.5 inches. At those depths, rainfall depths, pretty much anything that has a curve number less than 84, I think, by the NRCS method, which you're using, does not generate does not generate runoff. So by design, you're already kind of, because we're selecting this small frequent storm depth, we're eliminating runoff that we model from pervious areas. So we'd run this calculation where you're just, again, basing it off of the impervious acreage in square feet. Your precipitation is generally 1, and so you're just dividing it by 12 in order to get cubic foot volume. And this is so simple and so easy. And we've compared it to more, I guess, robust calculations. And I mean, they're statistically the same number for the reasons why I told you. And then we have other, that's the runoff coefficient that you see in many state manuals. Again, for the most part, if I want to back of the envelope calculation, I'm just using this. The other sizing method we see often is a ratio of the watershed area to filter area. I also call that the hydraulic loading ratio. And typically, like in the state of Maine, they do this and they require that bioretention systems be sized for no more than 5%. So that's a 20-to-1 ratio. So you have 20 unit areas of treatment to 1 unit area of system. And this could work. For the most part, if we're designing systems, we see that this hydraulic loading ratio goes much higher, even up in some cases up to 200-to-1. And these systems can handle it, but often though, I mean, there's some other design constraints around that. All right, so rights of ways, I kind of covered this a little bit. You know, in general, we're not putting these systems, if we're anticipating infiltration, we're not putting these systems in areas of high pollutant load, or we're lining them. We're also, in some of these we'll return to for when we talk about infiltration. There's lots of soil restrictions when we look at systems being installed according to some of the state manuals. But I wanted to just focus on slopes, because oftentimes we hear that these types of systems can't be installed in areas with significant slopes. And we have installed them in the past. Generally, what we do is we want the surface of the system to follow the landscape slope. So here, this is a roadway where we install the bioretention. The top of the media follows the 3% grade on the adjacent road, and we do that largely to maintain a consistent system. Otherwise, if we kept the surface flat, obviously we would have a huge hole in the front, and then we'd level out in the back, and we really don't want that. You know, think cars being trapped in the bioretention system. Not a good photo opportunity. So we like the top to follow the grade, but the bottom we design to be level. So the bottom gets terraced. So while the top follows the grade, our bottom basically steps down. And here we have basically 3 steps down. The system is about 100 feet at a 3% grade. Every 33 feet, we go down a foot or so, and we just terrace it. And so we have 3 basic bays here, and so that the bottom can remain flat. And we do that largely because what we worry about in terrace systems is concentrated and accelerated flow along the confining layer. So the confining layer in the bottom of the system would be where the stone meets the native soil. And if you don't have restrictions there, you can get accelerated flow along that layer, and you can get pushing and piping and soil disturbance, which affects the integrity of our system. So you can terrace. The other thing I've seen implemented is a geotextile, which again, I've already covered, does a great job at arresting flow. And sometimes it's just a zigzag back and forth and backfilled with stone. So it creates kind of a separation or internal check. All right. So I'm going to talk a little bit more about the soil mix, because this is something we see a lot of variability around. If you look at nationally, the standards, they range between 50 to 85% sand. And one thing that really hurts fire retention system design, or I'd say non-proprietary system design, is these soils, these have no specifications. We say sand. What does that mean? We say compost, or we used to. What does that mean? And so the variability here is chasm-like. Sand, what do we mean? Now we're trying to develop more standards around what we mean by sand. For the most part, we borrow industry standards on sand, and we say it should be a C33 sand, or something, a coarse sand, right, with a particle size distribution that meets that ASTM or DOT spec. And now we have some consistency of material. Does it have to be that? No. I mean, there's still some flexibility here where you can source local materials, but we're moving away from a straight sand, loam, wood chips by percentages, and we're going towards what I call a performance spec based on a particle size distribution. So you can use what you want. You arrange it in these general ratios, and then at the end, you do a particle size distribution on the final mix. And if it meets the criteria, and I'll show you that next, it's also on our website. If it meets the criteria, we remain relatively confident that that's going to perform hydraulically. One of the issues that we've seen with fire retention systems is leaching with respect to compost and use of compost. So we've detailed that. We have thesi on our website that detail this. University of Vermont has also published on this and shown that there's leaching from use of compost. And there's not a great workaround. So we can say, and we've been kind of compelled by our cooperative extension to include low P compost. And I'm happy to do that. What we say for is it's easy just to eliminate it and just to use a loam. If you want to use a low P compost like leaf compost, then make sure you put in your spec some testing requirements around that, because I can't tell you how many times we put low P compost, and then during an installation oversight, we take a look at the compost and I'm like, this isn't leaf compost. Where does it come from? Oh, it comes from Joe down the street. Not saying that contractors always cut corners, but it's the same thing with geotextile. I spec a woven geotextile, a Mirify certain number, and then I show up on site and, oh, I had an extra roll in the back, so I use that. Same difference, right? And so sometimes we're providing specifications in their design that aren't really honored during the installation, or need to be verified. So if you're going to use like a low P compost, the guidelines are it should have a P index of less than 30. And then we start to get, we can get kind of experimental with our compost loams and soil amendments. Sorry, I kind of skipped ahead of myself. Here's the particle size distribution that we've developed. Again, this is on our website. I might be able to show you that real quick. Let me see if I can do this. I'm playing with fire here. Playing with fire. Where did that go? No, I'm not going to do it, guys. UNHSC, Google it. We're the first thing that comes up. If you go to our pub specs and info, we have detail on bioretention soil mix. So it has sort of some of the ratios and components, and it also has a particle size distribution that, again, this is a way that you can test and make sure hydraulically that your system's going to stand up. Good. And then the last thing I think I'm going to talk about here is, I told you get rid of geotextile in the vertical cross section, and that means the unmaintainable layer. So if I put geotextile under 24 inches of bioretention soil mix, you're going to move heaven and earth before you get anybody to maintain that, right? You're going to have to excavate your whole entire system. Where this doesn't apply is when it's accessible or maintainable, such as in isolator rows in chamber systems. Oftentimes a woven textile is used in the isolator row, and that's fine. It actually does a great job of filtering. The woven textile is stronger and it doesn't clog as readily as the non-woven. And it creates we're finding it creates like an organic humus on top as it removes organic debris and other things that it accentuates phosphorus removal. Those are fine. You can open the hatch on a catch basin and you can get a hydrojet down there. It's accessible, it's cleanable, it's maintainable. A geotextile between the bioretention soil mix and the stone layer in a bioretention system is not. So we generally eliminate them. And what we use is a graded filter specification. So this comes out of Federal Highway. It's also used by the Army Corps of Engineers to, and it's basically just a inequality calculation between your fine materials above coarse materials. And if they satisfy these three inequalities, then it can perform as a setting bed, meaning you can be relatively assured that the particles, the fine materials won't pipe into the coarse materials. Generally, we use a pea stone as an intermediate layer. So if we use a 3/4 inch stone or 2 inch minus stone as a reservoir, which is fine, we layer it with 3 to 4 inches of pea stone, a 3/8 inch stone. And that has worked really well as a setting bed. If you're dealing with a system and you're not doing much reservoir, then just use a 3/8 inch stone. For the most part, I mean, if you got really nitpicky, a 3/8 inch stone has a void space of about 30%, and a 3/4 inch stone might have a void space of about 40%. So, I mean, pretty much the same. Now, amendments. Because of this phosphorus removal capacity and the lack of ability of, as we move these soils to higher and higher flow rate, and higher infiltration rate, means we go from more organic material, right? If you think of rain garden, a lot of it is 50% compost, 50% loam. That's going to have plenty of organic material, plenty of absorptive capacity, and it might even be leaching if that compost is not a low P compost. So what do? We don't want that happening in our phosphorus threatened waters. Now we have to look to some type of amendments. And this is where it gets fun, because you know, we can kind of Frankenstein these things together such that we're better addressing our pollutants of concern. So there's a lot of proprietary stuff out there, absorptive material for phosphorus binding, enhanced phosphorus scavenging. We found essentially zero valent iron and a drinking water treatment residual that we post-process to be really good and really cheap at scavenging phosphorus. There's a PhD that's finishing up at University of Vermont that's publishing on the use of drinking water treatment residual and basically confirmed what we had already found, that you can get anywhere from a 20 to 85 year lifespan out of the use of a drinking water treatment residual at about 5%. So same thing with a zero valent iron. I haven't really found a great source for this, but when I do, I'll let you know. I mean, outside of busting up a bunch of etch-a-sketches and sprinkling that stuff, a lot of times we only get access to like chemical grade, research grade zero valent iron, but there's got to be iron filings out there that are readily available that people are looking to get rid of. Just like the water treatment residual, we're paying to get rid of something that's about 99% water. So I'm going to cruise through this. This stuff is on our website, but these are some of the details for nitrogen. If you want to enhance nitrogen removal, what we're moving towards is what we call an internal storage reservoir. We're building a saturated zone within our system. And what this is looking at is a control and then various configurations of internal storage reservoir, and we're looking at nitrogen reduction. So if you look at just the median bars, this is the median on these box and whisker plots. If you're looking at just the median bars and you're looking across this here, lower is better. So we have our control that would be basically just water through the column. We have our influent concentration at about 1.7 milligrams per liter, and we're looking at a variety of different treatment devices. And what we're finding is we're altering the size of the storage reservoir. We're basically sizing the internal storage reservoir for a percentage of the water quality volume. So here you have 25% of the water quality volume, 50%, 75%, 100%. And we're looking at residence time. So how long do you detain the system? And you do this through some orifice control on the outlet. We'll go through this a little bit more as we go into gravel wetland. What this data is showing is that the detention time or retention time in the system is far more important than the size of the reservoir. So if we can hold it for longer periods of time, we get better removal, and we can shrink down the size of that internal storage reservoir. So we have a design specification for a hybrid bioretention system because we have nitrogen problems here in the coast, and so the criteria is enhanced nitrogen removal. And if you're in good soils, there's no way that you want to align that entire thing. So what we're building, and I don't think I have a picture of it, but again, on our website, what we're building is a first flow cell through what's essentially a subsurface gravel wetland in the middle of a bioretention system. And I'll go over that. We'll go over that a little bit more when we get into the gravel wetland. For phosphorus, we're using these media amendments. And here I'm showing you water treatment residual at 5% by volume of the bioretention soil mix, the BSM, 10%, and then iron filings at 3 and 6. And then we also looked at slag and limestone. The results here, again, we're really focusing on, this is no result. So here's our influent. And this is for phosphate. So this is what you're interested in if you need phosphorus scavenging, or probably Roger Williams Park is really interested in this. We should start testing some of these methods. But we found water treatment residual and covalent iron to be the best. The slag and the limestone really didn't do much. We've also seen the use of expanded shale aggregate, and it all comes down to cation exchange capacity. We've done studies on expanded shale. And what's interesting is they come from different parts of the country, and some parts are more, I guess, have a higher charge than others. We found the stuff coming out of New York to be really good, high cation exchange capacity, really good phosphorus removal. So just something to consider, that there's natural products that can be harvested, that can be used, that have this cation exchange capacity that we're basically amending with the use of polyaluminum chloride. Not to mention that it's a waste product. Again, that if we can reuse it, the university and their drinking water treatment plant will give this to us all day long. So very good removal here. And then, like I said, we've seen about a 20 to 85 year absorptive capacity with typical stormwater phosphorus loadings. So media thickness, often a question. Again, anywhere from 12 to probably 30 inches is what's most common. For the most part, because much of the function, much of the physical straining is happening within the top few centimeters, you're probably sizing media thickness more for vegetation sustenance. If you're using media amendments and you're increasing the residence time, you're largely doing that through some outlet control. So, orifice control or something in the outlet. You're not really designing that into your system. So I talked a little bit about this internal storage reservoir. For the most part, you can see a detail on our website where we're getting away because we have some empirical data on something that's 10% of the water quality volume. So our internal storage reservoir, the physical storage capacity in the length and width of this kind of first flush flow cell is 10% of the water quality volume. Sounds familiar, sounds a lot like our pretreatment sizing of our structural floor base. And we're finding that those do well as long as we can keep the residence time in there. And we also see that nitrogen is and phosphorus for that matter, is very first flush weighted, meaning it comes off in the first 1/10 to 2/10 of an inch. So what the plumbing of that looks like is basically in your reservoir stone, you're just creating a saturated zone with an elevated outlet. And oftentimes, if you're in good soils and you're lining this somehow, and you're lining it not only in the sidewalls, but you're lining it on the top, as what we're doing here is trying to create plug flow. So if you didn't have this liner in the middle, then water would come down and just short circuit this whole reservoir and go right to the outlet. So here we're basically creating this flow path that runs linearly along this liner that's installed at a negative slope into the stone, and then through 15 to 30 feet of flow through the saturated zone. So again, we've installed 2 of these, but our Department of Environment is requiring them more and more for nitrogen control. And it's exciting to see more engineers get into the business of doing this. It's fun. It makes the design a little bit more interesting. And, every time we install one, we learn a little bit more. Okay. To mulch or not to mulch. So I think Roger Williams Park is a no mulch facility. Is that right? Yeah. So I'm in the no mulch camp. There's plenty of people that I know that are in the mulch camp. I think it depends on your area, the level of maintenance you want to do, and how your crew is set up for maintenance. The thing, for my purposes, I'm usually designing larger systems that treat larger areas. And no matter whether the mulch is triple shredded, quadruple shredded, hardwood, softwood, wood floats. Wood floats. And so if we're directing a lot of flow into an area, we always see that mulch shift and push. And particularly it pushes to the back of our system where our high flow bypass contingencies are. And you can see some of that happening here. And this isn't even a mulch system. This is just normal debris from some of the vegetation, from some of the organic material that's been collected in here, pushed to the back. And it's usually why we use beehive structures as opposed to flat structures on our high flow bypass controls. If you use a flat surface, then you have one dimensional clogging front. If you use a dome, you have a multi-dimensional clogging front. So you can see I'm clogged here, but as the water rises, it's going to access because of the dimensionality of the dome. So something to consider. Drain downtime is another design contingency. Oftentimes we see bioretention systems, people wanting to use bioretention systems for also peak flow control. And so it's possible that you're building a larger basin, a smaller filter area within a larger basin, and you want to allow for more storage depth above the filter. That could, sorry, I skipped ahead. In general, we see ponding depths of anywhere from 6 to 24 inches. If it gets above 24 inches, then you're doing two things. One is you're potentially changing what types of plants might occupy your system. They need to be able to withstand that inundation. Two, you're also creating a driving head that could push material through your filter system and kind of push some of the fines out of your system. We did design a sand filter with a 6-foot ponding depth, and I wouldn't recommend it. It didn't get very good performance, and we felt that buildup of driving head kind of pushed stuff through that filter and led to lessening of the physical filtration capacity. So 6 to 24 inches in general. There are instances where you might be able to get away with more or less. I think at that point, it's just engineering judgment. I skipped over drain downtime. Typically, we use a 24 to 48 hour drain time. Like I said, for the most part, whatever sizing equation you're going to be using is likely going to be really conservative, and your system is going to drain far quicker than your infiltration rate times 0.5. And then vegetation. So I've really taken a laissez-faire approach to vegetation. My point would be, I'll take whatever I can get. We're so behind in stormwater management. I kind of feel like if you want to grass it, great. If you want to plant it, great. And this sounds kind of, I guess to some folks, it sounds like I'm a plant hater or something, but I just think we need to do more. I will illustrate some of the lack of detail, though, that's out there. There's not a lot of good sources for information on plants. In our manual, and I can pick on New Hampshire, when you go to the 2008 design manual, for plant selection, it tells you to use this national list of plant species that occur in wetlands in the Northeast. These are facultative wetland plants. And I guarantee you that none of the plants that you select here will survive in bioretention systems if you're designing it to the updated specs for soil. Because if your system is 50 to 85% sand, it's virtually a desert to facultative wetland plants. So it's kind of funny to me. This is still there. This is still in our manual. It's a good illustration of how much more research we need on the plant side. Most manuals are out of date like this. And I can't, if I save you a few $1,000s on plant species, then my job is done. Because I have seen $20,000 plants that were expertly spec'd out. These landscape architects know what they're doing. They're developing these microzomes, biozomes, different planting palettes, and they're putting a lot of time and effort into it, but they don't survive. And it's just mainly because we built a virtual desert for some of these plants, and we just need to get in step, I think, a little bit more on the plant species. What I've done, and this is what I recommend to people, is we seed. So I will go to New England Wetland Plants or another specialty seed company. I'll select a seed of the majority of species that I really want to populate, and I'll seed it. invariably what I wanted to come up likely won't come up, and something else will come up, but it will self-select. So if you go with a seed mixture, you can potentially self-select. If you're going with potted plants, then you gotta, the engineer and the landscape architect have to be lockstep, and they have to know what each other is doing. And oftentimes we'll work with a landscape architect to develop the plant palette, and I'll say, it's going to store 6 to 12 inches of water 24 to 48 hours. That's my design criteria. That's not what happens if it's 85% sand. What happens is it fills up and it drains, and any wetland species probably won't survive. So there's that. For trees, I put our link here. If you go to the front page of our website, we have a new report that it's not actually new, but it's new online. Again, with our urban forester that identified different tree species that could potentially be used in these tree filters. So that's something to take a look at. We haven't done a lot of research on it, but so I don't have my break in here, but I'm going to take a quick break since I've been going for about an hour, and see if there are any questions, and just give people just some time not hearing my voice.
So I've been monitoring the questions, Jamie, and they're all for you. So if we're going to answer questions, you're going to have to keep talking.
I can do it.
All right. The first question was, when you're doing pre-treatment designs and thinking about the ease of operation and maintenance, do you look at the life cycle of the practice? Do you do a life cycle analysis?
It's a good question. We've done some life cycle analysis. In general, it's not done. Oftentimes, life cycle analysis is a spreadsheet effort, and pretty much across the board, we assume a 20-year life expectancy. None of this is really informed empirically. Most of it, from my experience and to my knowledge, is just standard calculations. So I'd have to say no. But no, I think we should be doing that. We should be moving there. I just don't see that the field is there yet.
Okay. The next question, they're not all related, so I can't sort of group them, so I'll just run through them. Who is qualified to inspect systems? Is it just engineers? And we need a certification program for stormwater inspectors, is the question comment.
Yes, you're speaking my language now. There is a national program, EnviroCert. If you Google them, they have now they have certified professional erosion and sediment control, certified professional in stormwater quality, and now they have a certified professional in stormwater system inspection. So for the most part, what many states are doing is they're requiring a certificate, either a PE or one of these EnviroCert certificates for inspection. And those states that have operation and maintenance requirements, and there aren't many, this is another emerging field, it shows kind of how far behind we are, would require you to be qualified, either PE or certified professional in stormwater system inspection. That's EnviroCert. So that program exists. And so right now, one of those, but it's been one of my internal missions to get New England onto some kind of certified operation and maintenance program. University of North Carolina, my friend Bill Hunt down there has a program, and it's required by North Carolina DEP to go through this. And so that's a homegrown inspection process that I think we could replicate here in the Northeast.
Great, thanks. This question has to do with the curb cut practices. They say that there's good points about the difficulty of directing gutter runoff into a curb inlet. Are there any models or methods specific to curb inlets to assist with design?
Brian, do you have anything on that?
We've got some recommendations, not formally identified, but we've looked at the width of those. We've looked at the location, obviously, and it goes back to that point about whether you want all the water traveling down that gutter to go into the BMP, or if you want just the low flow and have the high flow go past. So in addition, inside the curb on the vegetated side, we've put many different types. We've used erosion control fabric, we've used pavers, we've used reinforced turf, a lot of different treatments for that inlet flume down to the forebay. And we're monitoring the success on that as well. So yeah, but one other thing I wanted to mention, Jamie, was the plant material in stormwater. You're absolutely right. Yeah, that's the biggest mistake I see designers making over the last 20 years. You know, you can put shrubs in, you can do bare root, which is a small plant material. Unless you control the water during construction, they don't heal in, you can't get them, they flow down to the end into the overflow structure. I've seen it time and time again. And I've had designers tell me, well, you can't plant that inside the basin because it doesn't like wet feet. You know, plants that like to be in moisture, they're just simply not. And a lot of times these areas are like frying pans. They're in the middle of paving, they just dry out too quickly. You should not be designing plants that like wet feet for infiltration basins. I agree 100%.
Yeah, and I think we'll get there. It's just, you know, in the continuum of innovation, you know, we talked a lot about the lagging design standards, and the plant material hasn't even moved, right? At least in the general literature. That's not to say that there aren't areas of expertise. I'm sure there are many landscape architects out there that specialize in this, but I also would speculate with some certainty that you know, there's this natural tension between the professional engineer and the landscape architect, because for the most part they don't always talk, and oftentimes, you know, like the landscape architect does just the two-dimensional dressing and the engineer does everything else, and then, you know, so the landscape architect doesn't have control over the design, and so they're just given the spot that might be optimal, might not be optimal, and they'll just say, yeah, do some plants there. So it's not, even our design process is kind of clunky. We're not all integrated yet.
That's a good point. So this is a question that's related to the same conversation. With the removal of compost and organic material, do you have any tips to ensure healthy plant growth in bioretention basins or bump outs?
Yes, so we found that the addition of the loam at 20 to 30% does give a fair amount of organic material to sustain the plant selection. Certainly if it's grasses or other forbs, you know, something that don't require a lot of nutrients, then you're okay. If you're designing some other plants that need something to start, I would be okay with, you know, initial fertilization. So as you're kind of planting, you know, you're fertilizing the hole or where the plants are going in, or even initially broadcasting fertilizer. For the most part, we don't do that, but what's the word I'm trying to find? I'm blanking. A low degrading fertilizer or slow release fertilizer could work. It's something that I've considered. I haven't looked at it. A lot of times we're monitoring these systems, so we're not doing any fertilization. But that's the one thing I'd say.
Yeah. Okay. Here's can you address mosquito breeding in these BMPs and how to either avoid standing water and design depths to prevent egg viability?
Yes, I can. So first, we're in the 21st century. We're largely not designing detention ponds anymore. So let's all agree that you know, detention ponds are not a sufficient treatment. Even retention ponds, for that matter, right? Retention ponds can be great. They can be landscape features. In Michigan, a lot of retention ponds are like the centerpiece of a subdivision, but they have to be maintained. once they go stagnant or once they eutrophy, then the whole ecological collapse occurs, which then facilitates more mosquitoes. So for the most part, we're designing systems that drain within 48 hours. The mosquito takes 72 hours to breed in standing water. So, you know, if we're draining these systems within 48 hours, we're eliminating the life cycle. The other thing is when we're developing wetland systems, we've kind of adopted a subsurface regime. So we're not allowing standing water, we're keeping the water in the subsurface. So that helps eliminate some of these vector issues. But I would say these vector issues are more pervasive in our historical detention and retention ponds.
Thank you. Can you retrofit infiltration areas with amendments to reduce phosphorus?
Sure. Sounds fun.
That came from Wenley. You can talk to her about it.
Yeah, just we'll develop a little pixie dust and you just sprinkle a little. No, I mean, we've been thinking of amending soils. Like we could till in water treatment residual, and that has an amazing phosphorus scavenging ability. I've often considered using wood chips and including like wood chips in my reservoir stone to provide a long-term carbon source for denitrification. You know, there's no limit to what we can do, and they have proprietary stuff. It sells for like $700. I think it's like $700 a cubic yard for this proprietary phosphorus sorbents material, but it's like an alum coated aggregate that you could just apply. You could also apply like a water treatment residual. They're doing that in Vermont on ag fields. They actually have their drinking water treatment plants producing amendable water treatment residual that they're asking farmers to broadcast to help bind phosphorus. So we do that in ponds that are eutrophic. We, drop alum that binds phosphorus and sequesters it in the benthic sediments. Very common treatment approach. So yes.
Great. Beyond accounting for increased precipitation, how are you considering climate change in design principles?
Ooh, I like that question. Thank you. It also touches on a little nerve that exists in the stormwater field. This idea that we need to be designing for climate change. And so this is a very touchy issue. I don't have time to give it justice. I would say two things. Fundamentally, all the climate change is happening in the extreme volumes. So at the edges, the 100-year event, right, is getting 35% higher in volume. We're not generally designing for the 100-year event. What we're designing for the most part, are the small frequent storms, which really have demonstrated no real shift with respect to frequency. So climate change is really at the extremes and is outside of generally our design concepts. Not to say that it's not important, and we need to talk about it, but we also have to talk about it with some levity. The other thing I'll say is when I put climate change on my table with pervasive increases in unmanaged impervious cover, that is what really sets my hair on fire. So climate change for me right now is something that we don't really consider. However, we're trying to address the disproportionate increases in impervious cover that are not managed properly. That's really altering the whole hydrologic regime far more than climate change is right now in our watersheds.
Thank you. We have somebody who just points out that APWA has a certification program as well.
For maintenance?
What's that?
For maintenance.
That's all it says.
Okay.
So maybe they can
Yeah.
add more content here. This question said, We try to divert runoff during construction to filtering infiltration area. However, if the sediment does enter the proposed BMP, what is the impact and remediation activity? How deep do we need to remove and replace the media?
Good question. I would say first, sequencing in construction is really important. We often see stormwater features built early, and I would advocate that in the sequencing, they should be built towards the end. Also, you can use your excavation as a temporary sediment pond for construction, and then dig it out and dress it up as you're demobilizing. That said, if you're needing to rehabilitate something, the good news is much of the clogging is at the surface. So I would say you have to dig off the top, and you'll know when you get to the good soils. You'll be able to see it. And I don't think you'll have to dig very deep. I've looked at systems that have been clogged for decades, and we dig down, and within the first couple of inches, we see that virgin design material, the nice sand right below the schmuck layer. So I think it should be pretty evident if it's a bioretention system. Is that right?
Yeah. So this is the last question that I have on the list here. Do you see using stormwater basins as pollinator habitat garden as a practical or even useful? I'd say Audubon does, but I'm interested in your thoughts.
Absolutely. I mean, I raise bees myself. I think, that's one of the ancillary benefits. And I don't want to misconstrue my message. And what I'm calling for is not a preclusion of any one system. What I'm saying is we need everything and anything, and we need it yesterday. Because our problems with lack of stormwater treatment are recalcitrant and pervasive. So what I'm not trying to do is preclude any one system. And oftentimes I look to the owner. And Brian, you can kind of back me up. If I'm not talking to you and I'm planting all kinds of things, and you own the system in perpetuity and I'm going to be handing over the long-term operation and maintenance, and I haven't included you or talked to you about what type of maintenance do you know how to do? What does your staff do? Then no matter what I design, I'm already going to be behind. Because if Brian has a fleet of lawnmowers and I do some pollinator species and they don't know how to take care of it, there's going to be an issue and my system is likely going to get mowed.
I think to back that up, Jamie's right. Our maintenance personnel in our first trainings, we talked about what could possibly be beneficial to this, what should not be in there, and then a much smaller palette of what was planted there, because they're not horticulturalists, they're maintenance personnel, and they don't have that background, and they probably never will get to that point. But I think pollinator gardens and those types of plant material, because of what we talked about earlier, we're not sitting in water any longer. So those are all possibilities.
Yeah, thank you. So I think what is emerging is a more open dialogue between the system owners and operators. And I mean, I'll be the first to say I'm a decade and a half into this consistent mistake of not talking to the owners and operators about their maintenance habits. So, that has to be reversed. It's slowly reversing, but I think the kind of learning there is we should be designing for the maintenance culture of the owner.
Absolutely.
That includes pollinator species. Like if I'm designing for someone who wants a pollinator garden, that's the versatility of the system. You can do it. But if you're designing a pollinator garden for someone who's mowing, that's where the issues come up.
Yep. All right, those are the questions that are on our question queue.
Great. All right, so we've got about an hour to get through the rest of it. And I'm just gonna, obviously, you can move about, take breaks whenever you want. So I'm not going to stop. I'll just keep going in the interest of time. But you won't insult me if you get up and depart and take a little break, and I won't even know. All right. So now moving into infiltration. Oh, wait. No, I'm still in filtration. I haven't even got to infiltration yet. All right. So I'm just going to talk a little bit about subsurface gravel wetlands because again, I think across the range of systems that we looked at, horizontal flow wetland systems, that's the subsurface gravel wetland, by far outperform everything. And it's largely because if you've ever heard of this concept of unit operations and unit processes, these subsurface systems have it all. They've got biological activity in the saturated zone. They've got plants. They've got bacteria on the roots of plants. They have sedimentation. They have filtration. They have it all. What they don't have is infiltration. Oftentimes, that's the preclusion here. These are best suited for poor soils. In some respects, that gives us another tool in the toolbox, because oftentimes we hear people say, you know, oh, I have hydrologic soil group D. I can't do anything. It's true, but you can't do any infiltration, but you likely can do a gravel wetland style system. That's where it's suited best. So the critical design elements really are some form of pretreatment. Again, it doesn't have to be structural. We've designed these with offline deep sump catch basins, and they work fine. We originally, I just published a paper that's on our website on the history of a gravel wetland. If you want to look into it, it was traditionally used as a wastewater treatment facility. And if you actually go back into the old days in South Burlington, John Todd, who worked with living machines, actually successfully treated 500,000 gallons of raw sewage through a wetland system filled with different microcosms and ranges of plants. And that's really where this emanates from. However, this application is very different. The key feature here is water moves horizontally through the subsurface of this system. And we studied a 2 treatment cell system. And we did 2 treatment cells largely because, the design specs were largely adopted out of the wastewater field. And we wanted the ability to shut something down if it got foul. So we could shut one of these basins down and route everything through one of the other ones. And I think that's a contingency that likely came up when they were considering, you know, back flushing these if they're being used for a wastewater type of application. That said, we've been asked over and over again, can it be one cell? Absolutely, it can be one cell. The criteria is largely that you have a hydraulically restrictive native soil. A liner or a compact soil liner can be used underneath these systems, and you have 30 feet of travel through the stone. Now, we don't have any data on these types of systems, but we have data on at least two cell systems, but it doesn't mean it can't be done. My thought is it's going to function virtually the same. But again, oftentimes, you know, permitting agencies want data, and we only have data for a 2-cell system. And so that's really what it looks like. So you have 10% of your water quality volume is in the pretreatment. If you have offline deep sump catch basins, then you're just sizing these 50%, 50%, and 50% of the, or 100% in a single basin system. The important thing is the water quality volume is stored statically in the basin geometry. So the geometry above the wetland system. And this is the common area that we see, because essentially your stone layer is saturated due to an elevated outlet. So this elevated outlet maintains a water level at the top of the stone. It's conceivable that you have some void space in your soils, and you could make that argument, but oftentimes we're also calling for wetland style soils. So, we're not anticipating vertical infiltration through the soils. That would largely tend to short circuit our plug flow. So we have some type of hydraulic inlet at the front. Here, it's a perforated standpipe. There's other configurations that I'll get into, and we want water to flow down into the system. Sorry, I think I'm waving my pointer in the wrong screen. Down through the system and horizontally through the saturated stone. So another picture of how this looks. The hydraulic inlet can be a perforated riser pipe. Generally, we don't perforate it in the soil, and then it's perforated in the stone. And there's some headers or distribution lines. We have kind of adopted a second strategy, and I'll get into that a little bit later. But for the most part here, you've got 2 feet of gravel, you got wetland soil on top, you need a hydraulic inlet, and you need an outlet. Everything else is really, really easy for these systems. You're statically sizing water quality volume in your basin geometry, and that's about it. So it's as close to pond design as you can get. The only thing that you're doing is you're building the stone reservoir, and you're building up, sub-base components of your pond, but everything else is the same as building a pond outside of the inlet and the outlet structures. And I'll get into that a little bit. So you need some type of way to get water into the surface. Again, we're speccing a wetland style soil. So we're anticipating that over time, this is going to seal up, and we really don't want this to function like a bioretention. We want it to be we don't want the soil to allow water in. We want the hydraulic inlet to convey all the water. What we've done since, because we do have some maintenance issues around with standpipes, they tend to accumulate, especially in the pollen seasons, gunk and other confining materials, the holes. We typically go with a drilled as opposed to slotted. We find that those work better, but often they can be clogged as well. And so typically we put those in as a backup, and our primary hydraulic inlet would be the spillway. And this is on our website, and it's updated in our new specification for gravel wetland. We have our stone, we have our intermediate P gravel layer, we have our wetland soil, and then around the influent spillway, we have rock armoring, like a rock apron, like riprap apron, and below the riprap, above the P stone, we have a woven geotextile. Now, this is a maintainable layer. So what I can do is every 3 years or every year, depending on the land use that this is treating, you basically pull back that riprap, pull out the woven fabric, and replace it. That's been a manageable maintenance operation for these style of systems, and I like the way that it really does maintain the type of plug flow that we want. Then we have the standpipe as a backup. So if we don't get out there as routinely as we want, we still have a secondary hydraulic inlet. And so this is kind of our go-to design now for the hydraulic inlet, hydraulic outlet. We've learned a couple of things. One is, if we're really looking at long-term and life cycle, we would like to be able to drain that saturated zone. So this outlet is elevated, but we'd like to have some type of bypass weir that we could potentially lift up and remove. So oftentimes this is taking the form of, we have a outlet structure and we drop a weir basically in that can be removed periodically. And when I say periodically, I mean, you'll know if your system is clogged by your inspection, and you could remove that weir wall so you could potentially flush out the system if there's like a flock or something. We have successfully clogged a subsurface gravel wetland when we did a propylene glycol study for an airport. We loaded propylene glycol, which is basically sugar, and the BOD went through the roof. I mean, that system just went into high gear, and it produced like a biofloc, essentially, that just clogged everything up. So we were able to take out that restrictive outlet and flush the system out into like a dirt bag or other retention device, so that we weren't discharging that to the wetland. So that we like there long term. And then the other real issue here is protecting the outlet. So I'm going to show you a picture first of what not to do. So this is one of our original outlet structures. So you can see the weir wall in there. We have a plug here that we can remove to drain the wetland. And then we have an ORIS for control that you can't see in the actual weir wall. This had an inlet. So here, the basin is basically here. And so the primary flow path is through the hydraulic inlet, through the subsurface, out through the standpipes, right? Subsurface through the orifice control on the outlet. And our high flow bypass is a cutout here in this structure. And it seemed logical enough. The issue is if you remember, our weir is right across the top. So our weir is right across here. And so our inlet allows all the debris to go in on the clean side, and I would say on the dirty side of the weir. And for the most part, we want that orifice in the weir to control the flow. And if we're allowing unfiltered water onto the clean side of the orifice, then we're asking for that to get clogged with debris. In the particular instance that I showed you, it was clogged by a particularly small frog. Sad story, but you know, it just goes to show it can get clogged with anything: straws, frogs, other debris that find its way in here. So you want to keep this clean, only receiving water from the filter area, and then the dirty side then has your graded inlet. It's the only real advancement to this that I've seen. Otherwise, a large outlet structure like this really works well. And it's the outside of the inlet, this is the only other design constraint. In between, it's just a hole with gravel and some soil. Additional details here. Again, a ponding depth is generally 18 inches. In some retrofit capacity, it could be more than that. For instance, if this were retrofitted into a detention pond, and someone asked about, can detention ponds be retrofitted? And absolutely, we could put a gravel wetland right down the middle of a detention pond to convey the water quality flow. Since the inlet and the outlet are in the same elevation, this is highly suitable for retrofitability. Wetland soil specification is something we've struggled with. So New Jersey has developed a spec for wetland soils, and we worked with them on that, and we work with some wetland scientists on that as well. The idea here is again, something high in organic material. We're not worried about physical filtration, so it's not majority sand. It can be made of all kinds of different material, including, you know, native cut from your project. We have developed a particle size distribution for the wetland soil. We found that originally in our spec, we had a hydraulic conductivity spec, the 0.1 to 0.01 feet per day was our conductivity spec, and it's nearly impossible to spec. So what we developed in order to spec this, and what we were seeing is high variability in materials. We saw people putting, like, just hauling out wetland material with large logs in it. And again, the idea here is that you don't have a particle size that's large enough to bridge the entire depth of the soil, to bridge the top with the stone surface. So if you have large logs that basically bridge from the surface to the stone, then that potentially short circuits the system. So what we did is we came up with a particle size distribution. This is in our spec that, again, is easier to specify and is easier to source. So again, much like where we went with the bioretention soil mix, this is a performance-based spec that is cheap. PSD tests are cheap and readily available. Okay, vegetation. Again, here with our first gravel wetland, we went with all kinds of wetland plants. We had a 53% die-off rate of our plants. So, we spent about $20,000 on different plants. $10,000 just went out the window. And so what we're advocating for now is a wetland pound mix, or a wetland plant mix, sorry. It's about $125 per pound, which will blow the contractor away. Our contractor could not believe, he thought, these were like illicit drug prices here. But we've had great success with this. And again, the conditions here, there should be a reservoir of water available in the subsurface, but not every potted plant or wetland plant, actively establishes itself in these systems. It's dry, intermittent storms, so you really have to be robust and develop good feet and roots to be able to tap into those wet reservoir. So I've even advocated for folks to just grass it so it's stabilized with like a contractor mix, and then generally species will volunteer. The risk there, of course, is if it's not densely populated with the type of wetland plants you want, then you're asking for invasives to volunteer, and they will. So for the most part, things that we've actively vegetated with this wetland mix we've had good luck with, and not a lot of invasives, because they're so densely populated that it doesn't give the invasives footing to come in. But if you're taking a more economical approach, just be aware that some of your volunteers might be invasive species. And then this is the last slide, just identifying, the potential for retrofitting basins. And essentially what we're talking about is just putting in right along the outlet structure, digging in these reservoirs. So we're taking a dry pond, for instance, we're digging in this preferential flow path, either 2-cell or 1-cell, and we're allowing the water quality flow to be flowing through this this zone here. And because we're not really altering the inlet or the outlet, these lend themselves to retrofitability. All right. So we got 40 minutes left. Any burning questions, Meg?
There's only one that's come in since we did the other ones. What are the key treatment and maintenance differences between a subsurface gravel wetland and a wet vegetated treatment system?
Oh, good question. So a wet vegetated system, I'm not sure what the maintenance criteria are for that. I mean, my guess is you develop a wetland system and you pretty much leave it alone. That's where the subsurface system, it lends itself to maintenance because it has a dry surface where you can get equipment into. So a wet basin, outside of pulling out invasives, I'm not sure that, and making sure that there's no hydraulic restrictions, I don't know what you're doing to it. Presumably, like in a retention pond, you're dredging sediments periodically every, say, 5 to 10 years. I haven't seen the same maintenance criteria for a wetland surface system. So the subsurface system, essentially what we're asking folks to do is every 3 years to clear out the vegetation. And that's not like taking it out by the roots, it's just cutting it back and taking the biomass outside of the system. Because we're designing this in urban areas to manage nitrogen and phosphorus. And especially in winter climates, when you get, you could consider vegetative uptake as a unit process as a temporary nutrient sink. It's not permanent, meaning that the plants, unlike bacteria, do not permanently transform the pollutants. They incorporate, or the nutrients. They incorporate the nutrients in the biomass and the organic structure of the plants, and they're susceptible to remobilization through decay or senescence, especially in the winter. So we found that about 3 years is the time that it takes that biomass to decay, because you have certain die-off every year that's natural. And in about 3 years, we actually tend to start to see a release of the bioavailable dissolved nutrients from these systems. So we advocate for you to cut the vegetation and kind of harvest it out of the system. And if you go on our website, there's actually a video of us maintaining our gravel wetland at our facility. So that's the difference in criteria.
There's one more point, if I could, Meg, on that. The wet vegetated swale, if there's not a good forebay that's going to contain your sediment, or if your sediment forebay, riprap or otherwise, gets inundated and that material starts to move down, and then there's a mechanical maintenance or removal, you get into the integrity of the design, because the maintenance personnel may not know where that sediment ends and the original material begins. So that's where we run into problems with removing sediment from vegetated areas, because you can't, it's a compromise to volume and design.
So there actually a couple more questions have come in. Sounds like there's an opportunity to retrofit old school detention ponds to subsurface gravel wetlands. Is that pie in the sky, and how much would that cost approximately?
Oh, well, is it pie in the sky? I don't think so, but I haven't done it. It's kind of on my bucket list to do. So if you have an opportunity and you'd be interested in working on that, I'd be 100% game. I think it would be fun. That said, maybe you call it pie in the sky because it hasn't been done yet that I know of.
Okay, then the last question is, can you talk a little about climate change impacts on water quality? I understand that flooding is and will be a big issue, but how specifically do changes in precipitation patterns affect pollutant loadings?
Yeah, so I'm glad you made that distinction. So flooding and water quality are two different issues. They get handled in two different ways and are really different engineering approaches. So what is the potential impact from water quality from climate change? I mean, while we don't see storm depth frequencies changing, right? So if I mentioned previously the water quality volume, we're not seeing statistical changes in that depth and the frequency and recurrence of that depth. That said, we are seeing strange patterns with precipitation. Like right now, we are in the middle of a drought that I've never seen. We're on record for New England anyway, is supposed to be getting inundated with water. And I would be, right? So the distribution, so the intensity and the frequency, the intensity is not changing, the frequency possibly is. And so, we're in a drought right now. And that means that you're getting more potential accumulation of pollutants on these impervious surfaces, and you're likely going to have a larger delivery when it does rain. So we always joke about Seattle has like a seasonal first flush. You think they go through a dry period, right? From whatever it is, what is it? It's like November to April or November to June or something. And then when it starts raining, it rains continuously nonstop. So you imagine those first rains are mobilizing lots of mass that's accumulated on these impervious cover. And then by, the end of the rainy season, you could eat off the pavement. Not really, but, figuratively speaking. So there's like that build up wash off characteristics might change. And that's the only thing that I can think of.
Good, thanks. That's all the questions.
Okay. All right, infiltration. So let me start by saying filtration and infiltration aren't independently exclusive. Most filtration systems also infiltrate. So there's only a few additional details here that we're going to be getting into. And, that said, infiltration is a huge unit operation that has the ability to correct a lot of the urban hydromodifications that are really causing a lot of the problems in our receiving waters. So our receiving waters are really suffering from a shift in hydrologic regime due to the proliferation of unmanaged impervious cover. It's changing the water cycle. And so the biggest tool in our toolbox to combat that is reintroducing that water, right? Changing and repairing the impaired hydrologic cycle. So it's a big tool in our toolbox. That said, there are some conditions around use of infiltration systems that we have to consider. Now, for the most part, we're using like a web soil survey. So USDA is probably the go-to resource. They have a web soil survey where you can locate any region in the country and you can get up-to-date information on what that soil type is. Now, granted, this is coarse, and it seems like it's been good enough up till now to use for design, but we always recommend geotechnical investigations, right? Because you're always bound to be surprised what's there versus what shows up on the web soil. One of the things that I see, and I haven't really had a solution to it, but it's potentially problematic moving forward, particularly for new development and redevelopment, is many state manuals have preclusions for use of infiltration in higher KSAT soils. So in New Hampshire, I think we cannot infiltrate in A soils that have a saturated hydraulic conductivity greater than 10 inches an hour. That's rough. That takes a big tool out of my toolbox, right? In Maine, it's even more restrictive. It's 2.56 inches an hour. And so I forget what it is in Rhode Island. Connecticut, I think it's 5 inches an hour. So if we can't infiltrate in these areas of good soils, then again, it takes a big tool out of our toolbox. And, primarily what I've been able to find out is this probably is adopted from citing wastewater treatment facilities, like point of use wastewater treatment facilities, like septic systems, home use septic systems. And it's probably really been adopted from that, right? Because if you're introducing sewage into an area of good soils, you're potentially threatening groundwater. Safe to say that stormwater has pollutant load export rates order 2 magnitude less than wastewater systems. So, we're not dealing with near the concentration, but that said, on average annually, we're probably putting more volume into the ground anyway than certainly a septic system. So anyway, it's an area for increased investigation. There's not a lot of data on stormwater infiltration systems. I did find this 30-year-old study where an infiltration basin was studied in France, and they looked at pollutant concentrations in various points, not only within the system, but outside the system. And they largely found that essentially, and this is with respect to metals, they largely found within roughly a foot in both the vertical and the horizontal, those pollutants, in this case metals, reduced from relatively high concentrations down to background conditions. That's what you're seeing here, within basically a foot of depth. So you have high concentrations on the surface, and then within 0.3 meters, roughly a foot, you see a reduction down to baseline conditions across the board. I anticipate this story looks similar for metals and any other sediment associated pollutant. Hydrocarbons, sediment, phosphorus. Where I don't think it holds is with respect to dissolved pollutants like nitrate or chloride. So here's the big contingency. If you have chloride impairments or nitrogen impairments, you might want to think about discarding water into the ground more carefully if those are your problems. Other than that, I think most pollutants are conservative and are demobilized within a foot or two of the system. There is one of the best literature reviews on this if you're looking for more information. And again, this is something this is just a shot across the bow. This is something that's going to continue to come up as we rely on green stormwater infrastructure to repair the impaired hydrology of our urban areas. Inevitably, we're going to have to put more water into the ground, and this has some potential consequences that largely hasn't been well studied. But there is a St. Anthony Falls laboratory at the University of Minnesota has done a literature review looking at the threat of groundwater contamination from infiltration systems, stormwater infiltration systems. And for the most part, what they show is, where is it? There's like one line in here. I don't know why I have all this verbiage. There's just one line, and it's this right here. It says, the appropriate information regarding the pollution risk associated with choosing infiltration and the often greater pollution risk of not choosing infiltration must be available to optimize and execute appropriate water resource management decisions. So there's another lit review that University of Connecticut, the NEMO folks have done that came up with the same exact conclusion, that the risk of not infiltrating are often greater than the pollution risks of choosing infiltration. Just something to consider as food for thought moving forward. If we have permitted entities that are precluding infiltration systems, this possibly has a risk that needs to be leveraged and studied more. That said, we're not putting infiltration systems in brownfield sites. We're not putting infiltration systems at gas stations or areas of high potential pollutant load. We're not putting infiltration systems adjacent to architecture that has a risk of flooding out. We're not putting infiltration systems in areas with acid mine drainage. We're not putting infiltration systems in areas that have karst geology. So there are a lot of real preclusions to infiltration that we have to honor. So that's kind of the background. I know I'm going kind of fast here because I'm looking at the time and I've got 20 minutes. I did want to talk about really quickly infiltration trenches because there's a permit trigger here. Infiltration trenches are defined by EPA as those systems which are deeper than they are wide. So most infiltration trenches are narrow, deep reservoirs, and they're considered, if your infiltration system is deeper than it is wide, it is considered by EPA to be a class 5 injection well. So I am not entirely clear what that means. I know it's an elevated permit threshold, but for the most part, I think you have to report it. And I think it goes on some list somewhere that I've never seen. So, you know, it's not that simple, obviously. And I don't mean to make light of this, but there is an additional permitting step of a Class 5 injection well if you're installing an infiltration trench. That said, EPA has considered green infrastructure, so anything like a bioretention or bioswale, as long as it has a vegetative component, to not trigger Class 5 injection wells. So there's a memo, I think it's like a 2011 memo on that from EPA that basically precludes a lot of the green infrastructure like bioswales that could be deciphered as an infiltration trench as not triggering Title 5. Title 5, Class 5, sorry. All right. That's the note on infiltration trenches. So I'm going to scream through here. Again, infiltration could take the form of a basin. It could take the form of, that would have, you know, obviously some soil media, reservoir or not, discharging into good soils, potentially. It could be subsurface chambers or subsurface pipe. Again, for the most part, these designs are blind to what creates your void space. Your void space could be in a basin, it could be in stone, it could be in soil, it could be in chambers, it could be in concrete, it could be in these milk crate structures. That's the only thing, if you've seen them, they're these stackable structures that kind of allow for load bearing capacity, but also create tremendous void space at lower cost. Whereas stone, you know, for the most part, Northeast, we use stone exclusively, but it's also relatively cheap. As you move more and more south, it gets more and more expensive. And it's possible some of these HDPE products or other prefabricated products give you a better dollar per void space delivery. Most chambers that go in, chambers are kind of taking off. That's a subsurface system because they're very easy to install. For pipe system, you need a crane. I mean, these large diameter pipes are hard to ship and they're hard to install. Same thing, large corrugated metal pipes, hard to ship, hard to install, special equipment. These chamber systems can be stacked and can be installed by 2 people. I think the chamber systems have really come off as a manufactured treatment device option for subsurface infiltration. For the most part, I would say you need a water quality treatment arm of this thing. The first flush generally goes through what the industry calls a isolator row, and this isolator row receives the first flush of water, most laden with pollutants, and again, it has geotextile, woven geotextile in between the chamber bottom and the underlying stone, and it's also wrapped in a non-woven textile to block lateral horizontal migration. And that becomes your filter and your maintainable component. It also protects the open stone that's based in the other areas. The chambers, in order to manage the peak flow, are just going over open stone. And of course, the isolated row prevents that from clogging because this is maintainable and accessible. All right. So oftentimes there's some type of field assessment, and this area has really exploded. The geotechnical investigations and assessment of infiltration capacity of native soils. Back in the day, we used to have the double ring infiltrometer. And if you've ever spent any time using one, you know the issues with using double ring infiltrometer. It takes massive amounts of water. If your soils are even slightly restrictive, it takes hours. And for the most part, we've had amuse meters come out, and there's all kinds of other updated field measurements that are quicker, require less water, and really accelerate, give you accurate, repeatable infiltration capacity. So I'll leave that there. And again, I would say the more site-specific data you have, the better. Just relying on USDA soil maps is not really great. And it's not really, you know, it's no longer really acceptable when citing infiltration systems. All right, permeable pavements. Permeable pavements are innovative. We've used them with great success outside of the poured in place pervious concrete in the Northeast. And they're relatively inexpensive. A lot of the expense is on the additional site maintenance or the site excavation. You know, for the most part, most pavements go in on a sub base of what, 18 inches maybe? Typical porous asphalt is going in with a minimum depth of about, sub-base depth of about 30 inches. So that's where a lot of the costs really are. Materials-wise, for the pervious pavement, permeable pavement versus the dense mix asphalt, for the most part, it's about 20% more. But it's also doubling as your stormwater management strategy. So your pavement surface is your pond. In a lot of respects, I think 10 years in or 15 years in, the word about permeable pavements is they're great. They can be implemented successfully. However, there's a lot of issues with long-term maintenance. And just on a personal note, the University of New Hampshire has per capita, probably the most permeable pavements per capita in the Northeast. And we've stopped doing it, largely because we maintain these structures while we study them and then hand them over to UNH facilities, at which case maintenance activity stops. And it's not always because it's just ignored. We've been having trouble finding operations that vacuum these pavements. And when we do find vacuumers that come out, a lot of times they're not really doing the due diligence that they need. A porous pavement that's been neglected can't just be maintained once with a vacuum sweeper. It has to be, there's restorative maintenance, i.e. maintenance that occurs to restore infiltration capacity after years of neglect, and then there's routine maintenance. So if you first install your system and you follow routine maintenance, then it's going to be relatively easy to keep on top. We definitely recommend about 2 times a year, largely around spring and fall, pick up debris, and that's pretty good. But if it's been neglected, then you're going to have to do restorative maintenance. So that's really where the shoe drops. With respect to pervious concrete, the shoe drops because they're now requiring, with poured in place pervious concrete, a 1-year curing time prior to application of salt. And we just can't get that in the Northeast. What the salt does is it attacks the alkali silica reaction, and we see within 2 years complete deterioration of the concrete binder. So you'll see spalling, and your pea stone that was used in the original mix completely devoid of binder. It's just loose on the surface. So that's a problem. So we've largely precluded the use, or I wouldn't advocate the use outside of, we have a sidewalk to nowhere that has never been used, never been salted, and is in pristine condition after 10 years. But the big issue there is it hasn't been maintained with salt. So if you have like ancillary parking that's not going to be used in the winter, or overflow parking or something, pervious concrete can be a really, really good application. It just can't be salted. And they say within the first year, but when we started out, it was 30 days, then it was 90 days, then it was 120 days, now it's a year. And we just haven't seen the long-term evidence that it's going to cure appropriately prior to the application of salt, which again destroys the alkali silica reaction, goes on forever almost. So there's no real definitive point at which you're successfully cured and you won't be susceptible to spalling from chloride application. I'm gonna have to cruise through this. There's a lot of information out there if you're looking for design specification. We have a specification, so does Napa. If you're looking at pervious concrete, like you're in the South or you're doing something that's not gonna be salt applied, the ICPI, the International Concrete Pavement Association, will nearly design the thing for you, especially if you're from the Northeast, because they're looking to get, sorry, that is permeable interlocking concrete pavement, which is different. Those are pavers. Those have no susceptibility to salt because they're not porous themselves. Where the porosity is in the joint space in between the pavers. So these are really nice. They're aesthetically pleasing. There's a lot of online support, again, from ICPI. And we've monitored installations for years and they work well. Interestingly, we actually had a site where it was set for a full-scale reconstruction of a building on campus. It had a permeable interlocking concrete pavement driveway and parking area. They pretty much during reconstruction, they pulled up the pavers. We had them pallet them and store them, and then we actually put them back. So kind of an interesting anecdote. These things can be reused, and we did that pretty successfully. We've been successful with machine application, installation by hand. The real issue is these things can be installed really quickly. Where it takes time is they don't always line up with the edges, right? A lot of times you have confinement, like a curb or some confinement on the edge, and the paver blocks don't always line up, so they have to be cut and reset. And oftentimes they use a different pattern for the edging than they do for the actual weave of the paver blocks themselves. So common pitfalls is less in the design for porous asphalt and it's more in the installation. That's where we see the issues happening. And again, maintenance. Oftentimes things don't get maintained. That's another pitfall. We have successfully rehabilitated these pavements though, and I'll show you some data on that. It's just, that's obviously rehabilitating the infiltrate capacity is more expensive than doing routine maintenance. So ounce of prevention is a pound of cure. So I talked a lot about where to use and not use any infiltration system. Same thing applies. When I look at a porous pavement system, it's no different than an infiltration system. It's just that our surface, our wearing surface, is our hydraulic inlet into our system. So it's really no different than a subsurface chamber. It's a different hydraulic inlet, but the properties of design are pretty much the same. All right, I'm gonna kind of cruise this just again for lack of time. For the most part, some of the cold climate considerations are depth of subbase materials. We usually use the 2/3, the total system thickness should be 2/3 of the max frost depth. Max frost depth here is generally about 48 inches, so our subbase is about 32 inches, and that's really the design constraint. So when we look at storage capacity within the void space of that 32 inches, it's massive and immense. So if you're in southern climates or you don't have this frost depth penetration requirement, then you should be sizing your subbase again to store your volume. So your instantaneously generated water quality volume. Lots of questions out there on porous pavement. I'm sure I'll see them in the chat, and hopefully I'll leave a little time to get to them. No, oh, it's 11:54. We have a whole specification on our website. If you're interested, it walks you through the design, it walks you through the installation, and it walks you through some of the oversight that needs to be done. Primarily, oversight is maintaining infiltration capacity of your reservoir course and its temperature thresholds, because the asphalt binder cools a lot quicker because it has less thermal mass. If you think about it, the aggregate that you're using eliminates pretty much any of the fines. So there's no sands, it's a coarse open graded aggregate, and thus it cools really quickly. And that's really that's what we're always combating during installation. A contractor that doesn't know what they're doing will line up the trucks, because that's what you can do with dense mix asphalt. For porous asphalt, within an hour and a half, that stuff starts cooling, and once it gets to a certain temperature, you really can't. It's about 165 degrees Fahrenheit. You should be rejecting the mix, because that's around cessation temperature. It's not going to compact. And they do not like it when you reject a mix. Okay. For geotextiles, the same thing as with filtration systems. We will use them on the bottom of our system if we're not anticipating, for instance, if we're worried about if we're on a clay soil, we will use a fabric for bridging, because we're not really expecting a lot of vertical infiltration into native subsoils. That said, I like the use of geogrids, even as a precaution. Oftentimes, at least in the Northeast, especially where there's active development and redevelopment, you don't necessarily know what you have subsurface until you open it up and until lots of water gets into it. What I'm saying is there's structures subsurface, like old like blasting casting areas or something that can contain voids that once you allow water into the soils will pipe. And if you have void space in the subsurface, it's gonna, you're gonna get sinkholes. So sinkholes have been the one thing that really has cropped up in asphalt or porous placements. And these generally happen around structures that don't get adequately compacted during installation. Think about structures, catch basin and others that you cannot, the compactor cannot get over. Those have to be hand compacted. And if they're not, or there's pipes and other structures that aren't hand compacted, that's where you're going to get soil piping. Alternatively, it's where you have things in the subsurface that contain voids that can get soil piping. So if you use a triaxial geogrid, it's really cheap in the subsurface. It's really cheap and a really good safety measure for things that you don't know are there, that are there. I want to end with maintenance, because one of the biggest things is the advance in sweeping technology. We had the privilege of being a testing site for this new high efficiency vacuum sweeper. It's called Triveris. There's other vacuum sweepers out there that's like Stormwater Compliance. They're out of Falmouth, Maine. They call theirs what is it called? The regenerative, the RVP something. They have their own system, right? These are really high efficiency sweepers, and they're pretty amazing. They've restored my faith, at least we can regenerate long clogged infiltration capacity of pervious pavements. This has a high efficiency vacuum jet on the front. Sorry. And I'll just play this video real quick. Okay, here we are at the Elliott Alumni Center. Can I fast forward it? Okay. Yep. Doing our yes, I can. Cleaning. So I'm just showing you initially. This is the runoff from this is a clogged pavement. Time of concentration about 3 minutes and 20 seconds. 3 minutes for the water, which is not infiltrating, to make it all to the. And it doesn't really look like much drain grate, which again we add as belts and suspenders. Not much hurt. So there's the Triveris. This has a high efficiency rotating pressure washer on the front and a high efficiency vacuum on this aperture that you see. There's the jets, the circulating jets. Really, really impressive. And this is afterwards, same hose, same infiltration rate, and essentially that's the limit of the flow. So then obviously we took data. I'm showing here, we find a broad range of age of pavements at the school, and the age of pavements is almost proportional to the infiltration rate. So again, oldest on the left, newest on the right. If we look at infiltration rates, it's almost the inverse, right? Anything above 10 inches an hour, we're considering failed, because 10 inches an hour, the method we use is C1701. It's an ASTM method for porous pavements, and there's some leakage out of just the equipment. You can't get 100% leakage. So 10 inches an hour is basically clogged. So then we look at the before and after of these areas that were cleaned, and we go from 1.27 inches an hour all the way up to 135 inches an hour. So pretty amazing restoration. And this is the Alumni Center that you saw. That had been clogged for about 4 years. This is the original pavement that we studied at the Stormwater Center, and that's been clogged for about 10 years. All right, so I'm gonna end there because I think I'm out of time. So I apologize for issues in the beginning, but hopefully I will stay around if folks do have questions, and I'll feel free to answer them. But thank you for your time and attention, and hopefully this was useful. Any questions?
I have one question here on the porous pavement. How expensive is maintenance using the Triveris, and would you reconsider the use of porous pavement with this equipment?
So, okay, the Triveris, I think they're selling those for about 200,000, and that's what you'd probably spend on a good vacuum sweeper, like an Elgin Whirlwind. The regenerative air vacuum sweepers are less expensive, 70 to 80,000 probably, but I've always been concerned that the regenerative air vacuum actually, they do a good job, again, if you're keeping up with the maintenance. But from a restorative perspective, I've always been concerned that we haven't seen an improvement or regeneration of infiltration capacity like I just showed you. And I've always been concerned that they actually pull particles and clogging deeper into the porous pavement. So that said, it's expensive, but again, we have to differentiate restorative maintenance versus routine maintenance. So routine maintenance, generally, I think, we've gotten this done. Oh, I'm spacing on the costs. I think it was around $300 per acre swept per trip. So, that's about, if you have an acre parking lot, you can get someone to zip around from a restorative capacity, for about $600 to $1,000 a year. For restorative, I think we got a quote for all of our parking lots on campus, and it was on the order of about $26,000. But again, that's neglecting things for 10 years and then restoring the capacity, just like you saw. We did kind of a postage stamp, but to do everything, it would have been, let's just say 30,000.
Great. I have another question here. How do you deal with stagnant standing water in lined forebays?
Yeah, I know. Forebays are designed to be dry, And in a lot of ways, the chemistry, you need them to be dry for the chemistry to work out and the appropriate removals. But they often settle and operate wet. Wet forebays are not good in my book. So I would elevate them so that they did dry out, because there could have been some settling. So you should retrofit them so that they're dry, and either you have to install a pipe that separates the forebay from the main treatment bay that drains them completely, or you have to elevate. If you do have a drain pipe like that, you have to elevate the forebay. That happens more often than not.
Great. Those are all the questions that I see. I wanted to mention that we had a couple of questions about getting your slide deck or getting a chance to see this whole thing again. And the
Yes.
slide deck will be up on the SNEP website. We'll put it up on the Innovation Center website as well. And there'll be a link to the full webinar recording so people can review the content on their own time.
Mhm.
And
And you just scroll through the first 20 minutes of silence, right?
that's right. I just want to say thank you so much, Jamie, for sharing all your expertise with us. It's amazing. We still have a lot of people part of this webinar. They've stuck it out all this time. It's a long time to sit looking at your computer. So it's we really appreciate all that you've shared with us.
Well, good. I enjoy it. And again, we hope to continue to offer these things, and we hope to slowly kind of feed in the content and the learning, because there is a whole a decade or two of learning from the Innovation Center.
Great. Thank you. Thank you.
Thanks, Jamie.
All right.